Every moment of human life unfolds inside a sea of light. From the glow of distant stars to the radiation released by atoms on Earth, space is filled with entities that carry energy without mass, travel without slowing, and arrive without revealing any internal structure. These entities are called photons. They are responsible for vision, heat, chemistry, communication, and the transmission of information across the observable universe. Yet despite their central role in nature, photons remain among the least intuitive objects ever studied in physics. A photon has no rest mass, no electric charge, and no measurable size. It cannot be opened, divided, or examined for internal components. No experiment has ever revealed layers, surfaces, or substructures inside it. And yet, photons ionize atoms, shape stellar environments, trigger biological reactions, and cross billions of light-years without degrading or transforming. Modern physics can describe how photons behave with extraordinary precision. But when asked what a photon is made of, the answer becomes unexpectedly subtle. This question is not philosophical. It is grounded in direct observation. Photons produced in laboratories behave in exactly the same way as photons that began their journey near the edge of the observable universe. Gamma rays detected by space telescopes, infrared light measured by deep space observatories, and visible photons recorded by sensors on Earth all follow the same rules. They propagate at a fixed speed, respond to gravity without resistance, and interact with matter in discrete, indivisible events. At no point do they exhibit behavior that would suggest the presence of internal parts. In everyday language, energy is often imagined as something stored inside an object. A compressed spring contains energy. A moving mass carries kinetic energy. But photons challenge this picture. They carry energy without mass, without volume, and without internal machinery. The energy of a photon depends entirely on its frequency, yet nothing inside the photon oscillates in a mechanical sense. This raises a fundamental problem. If a photon has no interior, then where does its energy reside, and what exactly is changing when light propagates through space? Over the past century, physicists have approached this problem from many angles. They have examined how photons scatter from charged particles, how their polarization remains stable across cosmic distances, how high-energy photons arrive in synchrony with lower-energy ones, and how no trace of internal deformation appears, even under extreme conditions. These observations converge on a single conclusion. A photon behaves not like a tiny object moving through space, but like a precise excitation of a field that fills all of space. This understanding reframes the original question. Instead of asking what a photon is made of, physics asks what kind of thing can carry energy, momentum, and angular momentum without containing any material structure at all. The answer emerges through quantum field theory, where particles are no longer treated as miniature solids, but as quantized disturbances in underlying fields. In this framework, the photon appears as the smallest possible excitation of the electromagnetic field, defined not by composition, but by behavior. The sections that follow explore this idea step by step. We will examine why photons show no internal structure, what actually oscillates when light propagates, how a particle with no body can possess spin, how energy can exist without mass, and why the familiar wave and particle descriptions both arise from the same underlying process. By the end, the photon will appear not as a mystery object hiding unseen components, but as one of the clearest examples of how nature encodes energy and information in the fabric of fields themselves. The absence of internal structure in the photon is not an assumption. It is the result of decades of measurement. When physicists test particles for size or composition, they rely on how those particles respond to forces, collisions, and fields. Objects with internal parts respond differently to acceleration, magnetism, and scattering because their components can shift relative to one another. Photons show none of these behaviors. No experiment has ever detected a response that would indicate layers, boundaries, or internal motion. One of the simplest tests involves timing. When light travels across space, photons of different energies move together. If a photon had internal regions that responded differently to motion or gravity, then higher energy photons would arrive slightly earlier or later than lower energy ones after long journeys. Observations of distant astrophysical events show no such effect. Light emitted at the same moment arrives together, even after traveling billions of light years. This consistency places extremely tight limits on any possible internal structure. Polarization offers another test. Light can be polarized, meaning the electromagnetic field oscillates in a preferred orientation as it propagates. If a photon were composed of internal parts, those parts could be disturbed differently by magnetic fields, plasma, or gravitational gradients. Over cosmic distances, this would cause polarization patterns to blur or rotate unpredictably. Instead, measurements of polarized light from distant galaxies and quasars show remarkable stability. The orientation remains intact across vast regions of space, consistent with a single unified excitation rather than a composite object. Scattering experiments reinforce this conclusion. When photons collide with electrons, nuclei, or even other photons at high energies, the results match predictions for a particle with no size and no internal content. The scattering patterns depend on energy, angle, and polarization, but not on any spatial extent. Facilities that probe matter at extremely small scales have never revealed a photon radius or internal dimension. If such a feature existed, it would have appeared long ago in these measurements. The behavior of photons in extreme environments provides further evidence. Gamma-ray bursts produce photons with energies millions of times greater than those of visible light. These photons travel across the universe, passing through interstellar gas, magnetic fields, and regions of intense gravity. Despite this, the signals arrive with timing and structure that match theoretical expectations precisely. No deformation, dispersion, or internal imbalance has ever been observed. The photon behaves as if it has nothing inside that could be disrupted. This stands in contrast to particles such as electrons. Electrons possess mass and charge, and their behavior reveals internal properties through magnetic moments and interactions. When electrons accelerate, they emit radiation in ways that reflect their underlying structure. Photons do not. They show no variation that would indicate internal features responding independently to external conditions. In the language of the Standard Model, this places the photon in a unique category. It is classified as a fundamental gauge boson with spin 1, meaning it is not composed of smaller constituents. Understanding this classification requires a shift in perspective. In classical thinking, objects are defined by what they contain. In quantum field theory, particles are defined by how fields behave. The electromagnetic field exists everywhere, even in regions devoid of matter. When that field changes in a specific quantized way, a photon appears. The photon is not something added to the field. It is the field expressing one of its allowed modes of change. This view explains why photons show no internal structure. There is nothing inside them because they are not containers. They are events, patterns of activity in a field that already fills space. Just as a ripple on water is not made of a separate substance from the water itself, a photon is not made of material distinct from the electromagnetic field. It is the smallest ripple that field can produce. From this foundation, a deeper question emerges. If a photon has no internal parts, then the familiar oscillations associated with light cannot arise from components moving within it. Something is varying as light propagates, but that variation does not belong to a structure inside the photon. To understand what is actually changing, attention must turn away from the photon as an object and toward the electromagnetic field itself. When light is described as an oscillation, the description can easily be misunderstood. The word suggests motion of something tangible, a component rising and falling, twisting or vibrating in place. But no experiment has ever detected anything inside a photon that could perform such a motion. The oscillation associated with light does not belong to an internal mechanism. It belongs to the electromagnetic field itself. The electromagnetic field is not an abstract bookkeeping tool. It is a physical entity that exists throughout space and time. It carries energy and momentum, responds to charges and currents, and propagates changes at a fixed speed. When light travels, what oscillates is the value of this field at each point in space as the disturbance moves forward. The photon represents the smallest indivisible unit of that oscillation. In classical electromagnetism, the field is described in terms of electric and magnetic components that rise and fall in a coordinated pattern. These components are not separate substances. They are two aspects of a single field whose behavior is governed by well-tested equations. In this picture, the oscillation does not occur inside the photon. It occurs across space itself as the field changes from one moment to the next. Quantum theory refines this description without replacing it. At very low energies, the electromagnetic field can exchange energy only in discrete amounts. These amounts are the photons. When a photon is present, the field is not continuously adjustable. It is changed by one full quantum. The oscillation still belongs to the field, but the energy it carries is quantized. This distinction resolves a long-standing confusion. Light appears wave-like because the field spreads through space according to wave equations. It appears particle-like because energy is transferred in discrete events when the field interacts with matter. Neither behavior requires a photon to possess internal structure. The wave behavior belongs to propagation. The particle behavior belongs to interaction. Historical experiments illustrate this clearly. When engineers built early radio transmitters, they found that oscillating currents in an antenna produced disturbances that traveled through space and induced currents in distant receivers. Nothing physical moved between the antennas. Only the electromagnetic field changed. Later experiments showed that when the transmitted power was reduced to extremely low levels, the energy arrived in discrete packets rather than as a continuous flow. These packets were identified as individual photons. The same principle applies across the entire electromagnetic spectrum. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays all arise from the same field. They differ only in how rapidly the field changes. A higher frequency means the field oscillates more quickly, and the associated photon carries more energy. Nothing inside the photon speeds up or slows down. The difference lies entirely in the rate of change of the field itself. This becomes especially clear in atomic interactions. When an electron in an atom transitions between energy levels, the surrounding electromagnetic field adjusts to the new configuration. That adjustment propagates outward as a photon. The energy of the photon matches the frequency of the emitted radiation with extraordinary precision. If the photon were made of internal parts, variations would appear depending on how those parts moved or interacted. No such variations are observed. The energy is fixed because the field change is fixed. Laboratory measurements confirm this picture with increasing accuracy. Lasers produce photons with extremely well-defined frequencies. Every photon in a high-quality laser beam carries the same energy because each corresponds to the same field oscillation rate. Detectors record these photons as identical events, reinforcing the idea that their identity is determined entirely by the field behavior, not by internal composition. From this perspective, the familiar language of vibration must be interpreted carefully. Nothing is vibrating inside the photon. What vibrates is the electromagnetic field itself, as the disturbance propagates through space. The photon is the minimal expression of that vibration, the smallest amount of field change that can exist as an independent event. This understanding leads naturally to another puzzle. Photons are observed to carry angular momentum, a property normally associated with rotation. Yet a photon has no body to rotate, no surface to twist, and no mass to support mechanical motion. To understand how angular momentum arises without internal structure, the concept of spin must be examined in a fundamentally different way. Spin is one of the most easily misunderstood properties in physics. The word suggests a small object turning around an axis, like a planet or a wheel. But this image breaks down immediately when applied to a photon. A photon has no mass, no size, and no internal structure. There is nothing that could physically rotate. Yet every measurement confirms that photons carry angular momentum. This apparent contradiction forces a deeper understanding of what spin actually represents. In quantum field theory, spin is not a description of mechanical motion. It is a fundamental property of how a field transforms under rotation. For the electromagnetic field, this property allows excitations to carry angular momentum even when no material object is present. The photon inherits this property because it is a quantized excitation of that field, not because anything inside it is turning. The evidence for photon spin appears most clearly in polarization. Light can be polarized linearly, where the field oscillates in a fixed orientation, or circularly, where the orientation rotates as the wave propagates. Circular polarization carries angular momentum. When such light interacts with matter, it can transfer that angular momentum in precise, measurable amounts. Experiments show that the amount transferred matches exactly what is expected for a particle with spin 1. This transfer does not arise from contact with a rotating object. It arises from the structure of the electromagnetic field itself. When the field twists as it propagates, that twist carries angular momentum. The photon is the smallest unit of that twisting pattern. Nothing inside the photon is responsible for the effect. The angular momentum belongs to the field configuration as a whole. Measurements using circularly polarized light provide direct confirmation. When photons strike small particles suspended in vacuum, the particles begin to rotate. The direction and rate of rotation depend on the polarization of the incoming light. The effect can be calculated precisely using the known spin value of the photon. The results match theory without requiring any internal mechanism within the photon. A key feature of photon spin is the number of states it can occupy. The photon has spin 1, but only 2 observable spin states. These states correspond to the 2 possible helicities, meaning the direction of the field's twist relative to the direction of motion. Massive particles with spin 1 exhibit 3 spin states because they can be observed at rest. The photon cannot. Its lack of rest mass means it always travels at the speed of light, and this restriction removes the 3rd state entirely. This absence is not a limitation of measurement. It is a direct consequence of relativity. For a massless particle, there is no frame of reference in which the particle is stationary. Without that frame, the additional orientation cannot exist. The photon's 2 helicity states are therefore not evidence of missing structure, but a reflection of its massless nature. Observations across cosmic distances reinforce this interpretation. Polarization measurements from distant galaxies, quasars, and cosmic background radiation show that photon spin properties remain stable over billions of light-years. If spin arose from internal components, interactions with magnetic fields, plasma, or gravitational gradients would disturb it. Instead, the polarization patterns remain coherent, indicating that spin is embedded in the field itself rather than in a physical body. High-energy experiments support the same conclusion. When gamma-ray photons interact with matter, the angular momentum transferred always matches the value predicted for a spin 1 excitation. No additional spin states appear. No evidence of internal rotation is ever observed. The photon behaves exactly as a field excitation should. Understanding photon spin in this way removes the need for misleading mechanical analogies. The photon does not spin because it contains something that turns. It carries spin because the electromagnetic field allows angular momentum to exist as part of its structure. The photon is simply the smallest unit in which that structure can appear. This realization has important consequences. It shows that properties often associated with objects can exist without objects at all. Angular momentum, energy, and momentum can belong to patterns in fields rather than to material components. The photon is one of the clearest examples of this principle in nature. With spin understood as a field property rather than a mechanical one, attention can shift to another equally counterintuitive feature. Photons carry energy and momentum despite having no mass. Understanding how energy exists without mass requires examining how the electromagnetic field stores and transports energy as it propagates through space. The idea that something without mass can carry energy initially appears contradictory. In everyday experience, energy is associated with moving objects, compressed materials, or heated substances, all of which involve matter. Photons violate this intuition. They have no rest mass, yet they can lift electrons out of atoms, heat stellar gas, trigger chemical reactions, and deliver measurable momentum to anything they strike. The resolution lies in understanding how energy is defined in physics. Energy is not limited to matter. Fields themselves can store and transport energy. The electromagnetic field carries energy whenever its configuration changes in space and time. A photon is the smallest possible amount of that transported energy. This becomes clear when examining how photons interact with matter. In the photoelectric effect, light striking a metal surface ejects electrons immediately. The effect does not depend on the total intensity of the light, but on its frequency. If the frequency is too low, no electrons are emitted, regardless of how many photons arrive. When the frequency exceeds a threshold, a single photon is sufficient to eject an electron. This demonstrates that the energy is delivered in discrete units, and that the energy of each unit depends only on the rate at which the field oscillates. The relationship between energy and frequency is exact. A higher frequency photon carries more energy because the electromagnetic field changes more rapidly. Nothing inside the photon speeds up. Nothing is compressed. The increased energy reflects a tighter pattern of field variation. This is why gamma rays can disrupt atomic nuclei, while radio waves cannot. The distinction lies entirely in the behavior of the field. Momentum follows the same logic. A photon carries momentum even though it has no mass. This momentum is revealed when light exerts pressure. Solar radiation pushes dust away from stars. Laser beams can trap and move microscopic particles. These effects are not caused by mass striking matter. They arise because the electromagnetic field carries momentum as it propagates. When a photon interacts, that momentum is transferred in a single event. The absence of mass places strict constraints on how photons move. A massive object can accelerate or decelerate because forces act on its mass over time. A photon cannot. It always travels at the same speed because the electromagnetic field supports only one propagation speed. This behavior does not depend on the energy of the photon. Low-frequency and high-frequency photons move together, a fact confirmed repeatedly through timing measurements of distant cosmic events. Observations of gamma-ray bursts provide some of the strongest evidence. These events emit photons across a wide range of energies at nearly the same moment. After traveling for billions of years, the photons arrive at detectors on Earth with no measurable delay between high-energy and low-energy signals. If photon energy were stored in mass or internal structure, different energies would propagate differently. The absence of any delay shows that energy resides in the field pattern itself, not in mass. This understanding also explains why photons do not lose energy simply by traveling. A photon does not gradually decay or dissipate as it moves through empty space. Its energy remains fixed until an interaction occurs. When a photon is absorbed, its energy is transferred completely to matter or to another field. There is no intermediate state where energy leaks away. This stability reflects the fact that the energy is not stored in a structure that can wear down, but in a pattern that persists unchanged. Cosmic observations reinforce this point. Photons from the cosmic microwave background have traveled since the early universe. Their energy distribution reflects conditions that existed billions of years ago. Aside from changes due to the expansion of space, which stretches the field pattern uniformly, the photons show no signs of decay or internal alteration. Their behavior matches the predictions of a massless field excitation with remarkable precision. Laboratory experiments reach the same conclusion on smaller scales. Precision spectroscopy shows that photons emitted by atoms carry energies that match theoretical predictions to extraordinary accuracy. Lasers produce streams of photons with identical energies and momenta. Detectors record these photons as sharply defined events, with no evidence of partial energy transfer or internal release. From every direction, the evidence points to the same conclusion. The energy of a photon is not stored inside it as a substance. It is a property of how the electromagnetic field changes. The photon is the smallest unit in which that change can exist independently. This realization raises another question that challenges classical intuition. If a photon carries energy and momentum without mass, and if it has no internal structure, then how should its size be understood? Can a photon be said to occupy a region of space at all, or does it exist only as a pattern that extends wherever the field disturbance spreads? The concept of size is deeply tied to objects. A size implies an edge, a surface, or a boundary separating what belongs to the object from what does not. When physicists attempt to apply this idea to photons, it immediately fails. No experiment has ever measured a radius, diameter, or spatial boundary associated with a photon. The reason is not a limitation of instruments, but a reflection of how photons exist. When a photon is detected, the interaction is localized. A sensor records a single event at a specific position. But this localization does not reveal the size of the photon prior to detection. It reveals only where the energy transfer occurred. The detection process does not measure an incoming object's width. It measures the probability that the electromagnetic field will interact at a given point. This distinction becomes clear in experiments involving extremely faint light. When individual photons are sent toward a detector, each arrival produces a sharp signal. No gradual spread appears across the detector surface. Yet when the same photons are allowed to propagate freely before detection, their behavior reflects a field disturbance that extends across space rather than a compact particle following a narrow path. Interference experiments provide some of the strongest evidence. When photons pass through a double-slit arrangement, one at a time, each photon produces a single detection point. Over time, these points accumulate into an interference pattern. The pattern indicates that each photon propagated through space in a way that involved both slits simultaneously. There is no meaningful sense in which the photon occupied a single narrow region during propagation. Its field disturbance extended across the entire experimental setup. Frequency does not define size either. A higher frequency photon carries more energy, but it is not smaller than a lower frequency photon. The difference lies in how rapidly the field changes, not in how far it extends. A gamma-ray photon and a radio photon can both occupy large regions of space during propagation, even though their energies differ enormously. Optical coherence studies reinforce this view. In carefully controlled experiments, single photons are sent through long optical fibers or complex interferometers. The coherence length, which describes how far the field disturbance remains correlated, can extend for many kilometers. This means that until detection occurs, the photon cannot be confined to a small region. Its presence is distributed along the path defined by the electromagnetic field. High-energy scattering experiments lead to the same conclusion. When photons interact with electrons or other particles at extremely small distance scales, the outcomes depend on energy and polarization, not on any physical diameter. If photons possessed a measurable size, scattering cross-sections would reveal that size. Decades of experiments at particle accelerators have found no such evidence. Astrophysical observations echo these results on the largest scales. Photons emitted from the surface of the Sun spread outward across space, filling volumes vastly larger than their region of origin. Photons from distant galaxies propagate across interstellar and intergalactic space, interacting with gravitational fields and plasma without exhibiting deformation or fragmentation. Their behavior is consistent with a field disturbance that spreads according to physical laws, rather than an object with a fixed shape. The cosmic microwave background provides a particularly striking example. The photons that make up this radiation field originated in the early universe and now fill space almost uniformly. Their distribution reflects the expansion of space itself. If photons had rigid boundaries, this uniformity would break down as regions expanded at different rates. Instead, the radiation remains smooth, consistent with the localized field excitations. Mathematical descriptions of photon detection capture this behavior precisely. Quantum theory does not assign a position to a photon in the same way it assigns a position to a classical object. Instead, it assigns a probability distribution describing where an interaction might occur. The photon exists as a spread of possibilities until the moment energy is transferred. At that moment, the event becomes localized, but the prior spatial extent is not something that can be measured directly. This explains why no instrument has ever observed a photon edge. There is no surface to detect. The photon is not a small object moving through empty space. It is a configuration of the electromagnetic field whose extent depends on how that field propagates. The notion of size applies to matter because matter occupies space. The photon occupies the field. With size understood in this way, the photon appears even simpler than before. It has no boundary, no interior, and no spatial dimension that can be separated from the field itself. Its identity is defined entirely by how the electromagnetic field changes as it moves. This leads naturally to a broader comparison. If the photon has no internal structure, no mass, no size, and no decay channels, then it may represent the simplest possible way energy can exist as an independent entity. To explore this idea, the photon must be compared with other known particles and excitations to see whether any share the same level of simplicity. Among all known particles, the photon occupies a unique position. Many particles are fundamental in the sense that they are not composed of smaller constituents, yet they still possess multiple internal properties that constrain how they can appear, transform, or disappear. The photon shows an unusual absence of such constraints. It carries energy, momentum, and angular momentum, but it is not required to preserve a fixed identity over time. It can be created or absorbed freely wherever the electromagnetic field allows an exchange of energy. This difference becomes clear when photons are compared with particles that make up matter. Electrons, for example, obey conservation rules that restrict how they can appear or vanish. In any isolated system, the number of electrons minus the number of positrons remains constant. Similar conservation laws apply to quarks through the strong interaction and to other particles through their associated fields. These rules arise because matter particles correspond to stable configurations that cannot simply disappear without leaving a trace. Photons are not bound by such a rule. The number of photons in a system can change without violating any fundamental conservation law. Photons can be emitted when atoms rearrange their energy states, absorbed when matter interacts with radiation, or created in pairs during high-energy collisions. They can also vanish completely when their energy is transferred to another system. What remains conserved is energy and momentum, not photon count. This behavior reflects the nature of the electromagnetic field. The field does not require a fixed number of excitations to exist. It can adjust continuously, producing or absorbing photons as needed to accommodate changes in energy. The photon therefore appears not as a persistent object, but as a minimal event in the life of the field. The simplicity of the photon becomes even more apparent when its energy is compared with the energy of massive particles. The mass of a proton arises from complex interactions among quarks and the strong field. The mass of an electron reflects properties of its underlying field and its coupling to other fields. These particles maintain their identity even when isolated because their fields support stable configurations. The photon has no such configuration to preserve. Its energy arises solely from the rate at which the electromagnetic field oscillates. Nothing inside the photon contributes additional energy. There are no internal degrees of freedom that can store or release energy independently. The entire identity of the photon is encoded in how the field changes. Neutrinos provide a useful contrast. Although they interact weakly and have extremely small masses, they still possess internal characteristics that allow them to change form. Neutrinos oscillate between different types as they travel, a behavior made possible by their mass and the structure of their field. Photons show no analogous behavior. A photon does not change identity as it propagates. It remains defined only by its frequency, direction, and polarization. Other force carriers also highlight the photon's simplicity. Gluons are excitations of the strong field, but they carry a type of charge that causes them to interact with one another. This prevents them from traveling freely over large distances. The photon carries no such charge. As a result, it can propagate indefinitely through empty space without interacting. Theoretical descriptions sometimes include a gravitational counterpart to the photon, known as the graviton. Like the photon, it would be massless and associated with a field that fills space. However, gravitons have not been observed, and their properties remain speculative. The photon, therefore, remains the only confirmed example of a massless field excitation observed across an enormous range of scales. Experiments reinforce this picture. When photons collide with sufficient energy, they can produce pairs of matter particles, such as electrons and positrons. In these events, the photons do not break apart into components. Instead, the energy carried by the electromagnetic field is converted into new field configurations corresponding to massive particles. The photon contributes no pieces because it has none. Precision measurements place extremely tight limits on any possible complexity. High-resolution spectroscopy shows that photons emitted by atoms have energies that match theoretical predictions to many decimal places. If internal degrees of freedom existed, small variations would appear. None have been detected. The photon behaves as a single, indivisible excitation every time it is produced. Cosmic observations support the same conclusion. Photons from the early universe still obey the same relationship between frequency and energy as photons produced today. Despite traveling for more than 13 billion years, they show no sign of decay, fragmentation, or transformation. This stability is difficult to reconcile with any model in which the photon contains internal structure. Taken together, these observations suggest that the photon represents the simplest way energy can exist as an independent entity. It is not matter. It is not a composite. It is not a stable object with an internal configuration. It is a transient expression of how the electromagnetic field responds when energy is exchanged. This conclusion leads to an important question. If the photon is so simple, and if it contains no internal structure at all, then how can it display behaviors that resemble both waves and particles? Understanding this apparent duality requires examining not what the photon is made of, but how fields behave when energy moves through them. The apparent dual behavior of photons has shaped physics for more than a century. In some experiments, light spreads, interferes, and diffracts exactly as waves do. In others, it arrives as sharply localized events, each transferring a fixed amount of energy. Classical intuition struggles with this combination because waves and particles are treated as mutually exclusive categories. The photon does not fit comfortably into either one. Early interference experiments revealed the wave aspect clearly. When light passed through narrow slits or reflected from thin films, the resulting patterns could be predicted using wave equations. Bright and dark regions form through constructive and destructive interference. No picture based on tiny solid particles could explain these results. Light behaved as if it were distributed across space. Later experiments challenged this view. When detectors became sensitive enough to register individual events, faint light no longer appeared continuous. Instead, energy arrived in discrete impacts. Each photon produced a single detection at a specific location, transferring its energy all at once. There was no partial absorption and no gradual accumulation. This behavior matched the expectations for particles. The conflict between these observations was resolved not by choosing one description over the other, but by recognizing that both arise from the same underlying process. The electromagnetic field propagates according to wave equations. Its disturbances spread through space, interfere, and diffract. But the field exchanges energy with matter only in quantized amounts. The photon is the smallest such amount. This distinction explains why wave behavior dominates during propagation. While a photon travels, it is not an object following a precise path. The field disturbance extends across space, and its evolution is described by the same equations that govern classical waves. The amplitude of this disturbance does not represent material density. It represents the probability that an interaction will occur at a given location. When an interaction happens, the description changes. The field transfers energy to matter in a single, indivisible event. An electron absorbs the entire quantum, or none of it. This produces the particle-like appearance of the photon at the moment of detection. The photon does not collapse from a wave into a particle. The field simply completes an energy exchange. Single photon interference experiments illustrate this principle with clarity. When photons are sent through a double slit one at a time, each photon triggers a single detection point. Yet after many photons have passed, the overall pattern reveals interference. Each event is localized, but the distribution of events reflects wave propagation. the behavior does not require a photon to split or to contain internal parts. It reflects how the field spreads and how energy is exchanged. The same logic applies across the electromagnetic spectrum. Radio signals spread over wide regions, reflecting wave behavior that allows receivers to detect signals even when not directly aligned. Yet each interaction with an antenna involves discrete energy transfer. At higher energies, X-rays and gamma rays follow the same rule. Their propagation reflects field behavior, while their detection reflects quantization. Astrophysical observations reinforce this interpretation. Light traveling from distant galaxies produces spectral lines, polarization patterns, and interference effects that require wave descriptions. At the same time, detectors record individual photon arrivals. Instruments aboard space telescopes routinely operate in regimes where photons are counted one by one, yet the overall data still reflect wave-like propagation. The apparent contradiction dissolves when wave and particle are understood as descriptions of different stages of the same process. Propagation is governed by the field equations. Interaction is governed by quantization. The photon is not switching identities. It remains a field excitation throughout. This perspective also explains why no internal structure is needed to account for dual behavior. Classical particles behave as particles because they are localized objects. Classical waves behave as waves because they are extended disturbances. A photon is neither. It is a quantum excitation of a field that supports both extended propagation and discrete interaction. Probability plays a central role in this description. The field disturbance associated with a photon defines where interactions are likely to occur. The square of the field amplitude determines the probability distribution. This distribution evolves smoothly through space according to wave equations. When an interaction occurs, one outcome is realized. The rest of the distribution no longer applies because the energy has been transferred. This interpretation has been tested repeatedly. Experiments using interferometers, beam splitters, and detectors show that individual photons behave exactly as predicted by quantum field theory. No additional assumptions about hidden paths or internal mechanisms are required. The same framework explains interference, diffraction, polarization, and discrete detection. The wave-particle distinction therefore reflects limitations of classical language rather than a dual nature within the photon itself. Light behaves in ways that exceed the categories developed for everyday objects. The photon is best understood not as a wave or a particle, but as a quantum of field energy whose behavior depends on context. This understanding also clarifies how photons can become entangled. Entanglement does not require particles to send signals or share internal components. It arises from correlations established in the field during their creation. These correlations affect the probabilities of future interactions without implying any internal structure inside the photons themselves. As experiments have grown more precise, no deviation from this picture has been found. From laboratory interferometers to deep space observations, the same pattern emerges. The electromagnetic field propagates continuously, while energy exchanges occur discretely. The photon embodies both aspects because it is defined by the field. With this dual behavior understood as a natural consequence of field dynamics, the description of the photon becomes remarkably consistent. It has no interior, no boundary, and no mass. It propagates as a field disturbance and interacts as a quantum. These features point toward a unified description offered by modern physics. Modern physics does not begin by defining particles. It begins by defining fields. According to quantum field theory, every type of particle corresponds to a field that exists everywhere in space. These fields are not optional features added to the universe. They are the fundamental entities from which all observable particles arise. Matter particles appear when their associated fields form stable, localized patterns. Force-carrying particles appear when their fields change and propagate. The electromagnetic field is one such field. It fills all of space, even in regions where no light is present. When the electromagnetic field remains in its lowest possible energy state, no photons are observed. When the field is disturbed in a specific quantized way, a photon appears. This disturbance is not layered on top of space. It is a change in the field itself. In this framework, the photon is not a thing moving through space. It is a mode of the field propagating through space. Its energy is determined by how rapidly the field changes. Its momentum is determined by the direction of propagation. Its polarization is determined by how the field oscillates. None of these properties require an interior or a boundary. This description explains why photons behave identically regardless of how they are produced. A photon emitted by an atom, generated in a laser cavity, or released during a cosmic explosion, is the same kind of excitation. The field supports only one basic type of electromagnetic quantum. Differences in energy and polarization reflect differences in the field's motion, not differences in composition. The mathematical description of the electromagnetic field includes operators that create and destroy photons. These operators do not assemble particles from parts. They change the energy state of the field. When a photon is created, the field moves to a higher energy configuration. When a photon is absorbed, the field returns to a lower energy configuration. The process involves no internal rearrangement because there is nothing internal to rearrange. This view also explains why photon number is not conserved. The electromagnetic field does not require a fixed count of excitations to exist. It adjusts continuously as energy flows between systems. What remained conserved is energy, momentum, and angular momentum. The photon appears or disappears as the bookkeeping of the field changes. Quantum field theory further clarifies why photons cannot be isolated and examined like objects. A photon does not have a rest frame. It cannot be brought to a halt. It cannot be placed on a scale. Any attempt to confine it tightly enough to assign a position inevitably changes its energy and momentum. These limitations are not experimental flaws. They arise from the nature of massless field excitations. The absence of internal structure follows naturally from this description. A field excitation does not contain parts any more than a wave on the surface of water contains smaller waves inside it. The excitation is defined by the field's behavior as a whole. Attempting to locate an interior within it misunderstands what the excitation represents. This perspective also unifies all previously discussed properties. The lack of size, the stability of polarization, the fixed relationship between energy and frequency, the absence of decay, and the persistence across cosmic distances all follow from the same principle. The photon is not built. It is expressed. Experiments across physics continue to confirm this description. Precision tests of electromagnetism show no deviation from field-based predictions. High-energy collisions reveal no substructure. Astronomical observations show photons arriving unchanged after traveling through the most extreme environments known. The consistency across these scales suggests that the field description is not an approximation, but a deep feature of nature. When physicists speak of particles as excitations of fields, they are not using metaphor. They are describing the most accurate framework available. In this framework, the photon stands out because of its simplicity. It is the cleanest example of how energy can exist without matter, structure, or substance. This understanding reframes the original question one final time. Asking what a photon is made of assumes that it must be assembled from components. Modern physics suggests a different answer. The photon is not made of anything. It is what the electromagnetic field does when energy moves from one place to another. With this picture in place, the behavior of photons across the universe becomes less mysterious. Their ability to travel immense distances without change, to interact cleanly and precisely, and to reveal information about distant environments all arise from the same underlying simplicity. The photon carries no baggage. It has nothing that can be worn down, distorted, or rearranged. What remains is a single, consistent idea. The photon is a quantum of the electromagnetic field. It has no interior, no boundary, and no mass. It exists only as long as the field carries energy in that particular mode. When the energy is transferred, the excitation ends. From this viewpoint, light becomes not a stream of tiny objects, but a pattern of field activity unfolding across space and time. And the photon becomes one of the clearest demonstrations that the universe does not require complex building blocks to produce complex behavior. Sometimes the simplest possible excitation is enough. Once the photon is understood as a pure excitation of a field, its role in physics begins to look less like an exception and more like a reference point. It provides a clear example of how nature encodes energy and information without relying on material components. In doing so, it offers insight into how other particles and forces may arise from similar principles, even when their behavior appears far more complex. In quantum field theory, matter particles are not fundamentally different in kind from photons. They are also excitations of fields. The difference lies in stability and confinement. An electron corresponds to a stable configuration of its field, one that can persist even in isolation. The photon corresponds to a transient configuration, one that exists only while energy is being transferred. This contrast helps explain why matter accumulates and light passes through. The simplicity of the photon highlights this distinction. Because it has no rest mass, it cannot form a stable, localized configuration. It must propagate. It cannot remain in place or orbit quietly. The electromagnetic field does not support static photon states. Any excitation of that field necessarily moves. This requirement is not imposed by the photon itself, but by the structure of the field. This property has profound consequences. It means that information carried by light is always in motion. Signals encoded in photons cannot linger. They must travel outward at a fixed speed, distributing energy and information across space. This behavior underlies communication, vision, and nearly every method by which the universe reveals itself to observation. The photon also illustrates how forces operate without direct contact. Electromagnetic interactions occur through the exchange of photons, yet these exchanges do not involve particles colliding like solid objects. Instead, the field adjusts as energy flows between charged systems. The photon acts as the minimal unit of that adjustment. It is not thrown from one charge to another. It emerges from the field configuration shared between them. This view replaces older mechanical intuitions with a more coherent picture. Forces do not require invisible projectiles bouncing between objects. They require fields that respond to changes. The photon is the signature of that response in the electromagnetic case. Its existence marks the moment when the field rearranges itself to accommodate energy transfer. The absence of internal structure plays a critical role here. Because the photon contains no parts, it does not fragment or degrade as it moves. It cannot lose coherence internally. Any change in its behavior must arise from interaction with external systems, not from internal dynamics. This makes the photon an exceptionally reliable messenger. It carries information about its origin with high fidelity. Astronomy depends on this reliability. Light emitted by distant stars and galaxies encodes information about temperature, composition, motion, and magnetic fields. That information survives the journey across space because the photon has nothing inside it that can scramble or distort the signal. The field excitation preserves its defining properties until interaction occurs. This also explains why photons are sensitive probes of extreme environments. When light passes near massive objects, its path bends. When it moves through magnetic fields, its polarization shifts in predictable ways. These effects arise not because the photon is being deformed, but because the field through which it propagates is shaped by external conditions. The photon responds cleanly because it has no internal complexity to mask the response. In laboratory physics, the same principle allows photons to be used as precision tools. Lasers rely on the uniformity of photon properties. Spectroscopy depends on the exact relationship between frequency and energy. Quantum optics exploits the ability to produce and manipulate single photons with well-defined characteristics. None of these techniques would work if photons contained hidden structure or unpredictable internal behavior. The photon also provides a template for understanding why some fields behave differently from others. The strong field, for example, supports excitations that interact with one another. This leads to confinement and complexity. The electromagnetic field does not. Its excitations propagate freely. The contrast reveals how small differences in field structure can produce vastly different physical outcomes. At a deeper level, the photon challenges the idea that reality must be built from objects. If one of the most important carriers of energy and information in the universe has no interior, no surface, and no mass, then object-based thinking becomes optional rather than essential. Fields, patterns, and interactions take precedence over components and assemblies. This shift in perspective has influenced modern physics profoundly. It has led to descriptions in which particles are secondary, emerging from deeper structures, rather than serving as foundational building blocks. The photon stands as one of the clearest cases where this approach succeeds without ambiguity. The behavior of the photon also sets constraints on new theories. Any extension of known physics must reproduce the photon's observed simplicity. It must account for the absence of size, the stability of polarization, the lack of dispersion across energies, and the exact relationship between frequency and energy. These requirements severely limit speculative models. The photon's behavior acts as a filter that discards ideas incompatible with observation. Even proposed modifications to spacetime itself must respect these constraints. Some theories predict that high-energy photons should travel at slightly different speeds than low-energy ones. Observations have placed extremely tight limits on such effects. The fact that photons of vastly different energies arrive together from distant events suggests that spacetime treats field excitations uniformly. Once again, the photon's simplicity imposes order. As this picture continues to develop, the photon remains central not because it is mysterious, but because it is clear. It shows how much can be achieved with minimal assumptions. A single field, governed by simple rules, can produce phenomena that span from atomic transitions to cosmic structure. With this understanding, the original question can be viewed from a new angle. Asking what a photon is made of presumes that it must be assembled from constituents. The evidence points elsewhere. The photon is not assembled. It is expressed. It is what remains when energy moves through the electromagnetic field in the most elementary way allowed. This insight prepares the ground for examining how photons behave under the most extreme conditions known, where fields are distorted by gravity, density, and motion on cosmic scales. In these environments, The simplicity of the photon is tested not by isolation, but by exposure to the universe at its most intense. When photons travel through regions of intense gravity, their behavior provides some of the clearest evidence that they are governed by fields rather than by internal structure. Gravity does not act on photons by pulling on mass. Instead, it alters the geometry of space-time itself. The photon responds not by resisting or deforming, but by following the curvature imposed on the field through which it propagates. This effect is observed directly through gravitational lensing. Light from distant galaxies bends as it passes near massive objects, such as galaxy clusters or black holes. The bending does not distort the internal properties of the photon. Its frequency, polarization, and coherence remain intact apart from predictable shifts tied to space-time geometry. The photon behaves as a field excitation moving along curved paths, not as an object being tugged or stretched. Near black holes, this behavior becomes especially revealing. Photons emitted from hot gas orbiting close to an event horizon experience extreme space-time curvature. Their paths loop, spiral, and sometimes escape toward distant observers. Yet even under these conditions, the photons retain the same fundamental characteristics. They do not fragment or lose identity. The field excitation remains coherent until it is absorbed or escapes. Observations from modern telescopes have confirmed this with remarkable precision. Polarized light detected from regions near supermassive black holes shows patterns that match predictions based on electromagnetic fields propagating through curved spacetime. The polarization encodes information about magnetic fields and motion near the event horizon. That information survives because the photon carries no internal structure that gravity could disrupt. Gravitational redshift provides another test. As photons climb out of deep gravitational wells, their frequency shifts to lower values. The energy change does not occur gradually through internal loss. It reflects a change in how the field is measured by observers at different space-time locations. The photon itself remains a consistent excitation. The field configuration adjusts relative to the surrounding geometry. The early universe offers an even more extreme environment. Shortly after the universe became transparent, photons decoupled from matter and began traveling freely through expanding space. These photons form the cosmic microwave background observed today. Their uniformity and precise spectrum provide strong evidence that they propagated as simple field excitations through an evolving spacetime without developing internal complexity. As space expanded, the wavelengths of these photons stretched. This stretching did not tear the photons apart or alter their structure. It changed the scale of the field disturbance uniformly. The energy decreased in a predictable way tied to expansion, not to decay. This behavior again reflects the absence of internal components. There was nothing inside the photon to resist or fragment. High-energy astrophysical environments provide similar tests. Jets emitted from active galaxies accelerate particles to extreme energies and generate intense radiation. Photons produced in these jets travel across vast distances through magnetic turbulence and intergalactic plasma. Despite this, their arrival patterns match field-based predictions. Their polarization and timing remain consistent with simple propagation. Gamma-ray bursts offer some of the most stringent constraints. These events release photons across a wide range of energies in a short interval. After traveling for billions of years, the photons arrive nearly simultaneously. Any internal structure would produce energy-dependent delays. None are observed. The photons behave as if they are governed by a single, universal rule. Laboratory experiments mirror these cosmic tests on smaller scales. Precision interferometers measure how light responds to tiny distortions in spacetime. Gravitational wave detectors rely on the stability of photons traveling along long arms. The sensitivity of these instruments depends on the absence of unpredictable internal behavior in the photons themselves. Their success confirms the field-based description. In all these cases, the photon serves as a probe of space-time rather than as a participant with internal dynamics. It responds to geometry, fields, and boundaries without altering its identity. This makes it an ideal messenger from regions otherwise inaccessible to direct measurement. The consistency of photon behavior across such extremes reinforces a central conclusion. Whatever a photon is, it cannot be a composite object. It must be something that remains unchanged under conditions that tear apart atoms, disrupt nuclei, and warp space-time itself. The only description that satisfies this requirement is that of a pure field excitation. This perspective also constrains attempts to unify physics. Any theory that modifies space-time or introduces new structures must preserve the observed behavior of photons. Their simplicity leaves little room for hidden layers or additional properties. The photon's behavior acts as a benchmark against which new ideas are tested. As observations extend further back in time and deeper into extreme environments, the photon continues to behave in the same way. It propagates, interacts, and transfers energy according to rules that do not depend on composition. This reliability allows physics to connect phenomena across scales that differ by many orders of magnitude. With this understanding, the photon emerges not only as a carrier of light, but as a diagnostic tool built into the fabric of the universe. Its simplicity allows complex environments to be read with clarity, and its behavior confirms that fields, rather than objects, form the deepest layer of physical description. At this point, the behavior of the photon no longer appears fragmented across separate properties. Its lack of mass, absence of size, stability across cosmic distances, fixed relationship between energy and frequency, and consistent response to gravity all arise from a single underlying fact. The photon is not a thing built from parts. It is a mode of change in a field that fills space. This realization reshapes how simplicity is understood in physics. Simplicity does not mean lacking influence or importance. The photon is responsible for nearly every process through which energy and information move in the universe. It drives chemical reactions, regulates planetary climates, transports signals, and allows matter to interact across distance. Yet it accomplishes all of this without possessing internal structure. Its power comes not from complexity, but from consistency. In earlier eras of science, explanations often relied on hidden mechanisms. When something behaved in a puzzling way, it was natural to assume unseen components were at work. The photon challenges this instinct. Decades of increasingly precise experiments have not revealed hidden layers. Instead, they have repeatedly stripped the description down to something more elemental. The photon behaves exactly as a field excitation should, and no more. This has implications beyond electromagnetism. Modern physics increasingly treats all particles as expressions of fields rather than as miniature objects. In this view, matter arises where fields form stable, localized patterns. Forces arise where fields exchange energy. The photon occupies a special place in this framework because it shows what happens when a field supports change without confinement. It becomes motion itself. The absence of rest mass is central here. Without mass, there is no frame in which the photon can be stationary. It cannot settle into a localized configuration. It must propagate. This requirement is not imposed by external conditions. It is built into the structure of the electromagnetic field. The photon exists only while energy is in transit. This explains why photons are always associated with interaction. They appear when atoms change state, when charges accelerate, when fields rearrange. They disappear when energy is absorbed. There is no static photon waiting in space. There is only the field and the possibility of excitation. The idea that something can exist only as motion runs counter to everyday experience. Objects persist, whether or not they are interacting. Photons do not. Their existence is inseparable from process. This makes them difficult to picture, but also remarkably clean in behavior. There is no hidden reservoir of energy, no internal clock, no mechanism that can drift or degrade. This cleanliness is what allows photons to serve as precise messengers. The light arriving from distant galaxies carries information encoded in frequency, polarization, and timing. That information survives because the photon has no internal degrees of freedom that can scramble it. The field excitation remains faithful to its origin until interaction occurs. Even when photons participate in complex processes such as scattering, absorption, or pair production, the underlying description remains the same. Energy moves from one field configuration to another. The photon does not break apart or reorganize internally. It simply ceases to exist as that excitation once the energy has been transferred. This perspective also clarifies why the question of composition ultimately dissolves. Asking what a photon is made of presumes that it must be assembled from smaller elements. But fields are not assemblies. They are continuous entities whose excitations are defined by allowable patterns of change. The photon is one such pattern. When this is understood, many apparent mysteries fall away. Wave-particle duality becomes a matter of context. Size becomes a property of propagation rather than of substance. Spin becomes a feature of field symmetry rather than of rotation. Energy becomes a measure of change rather than of stored material. What remains is a description that is both minimal and sufficient. The photon is the smallest unit in which the electromagnetic field can carry energy and momentum. It has exactly the properties required to do this, and no more. Every attempt to assign additional structure has failed, because none is needed. This is why the photon continues to occupy a central role in physics. It is not only important because of what it does, but because of what it reveals. It shows that the universe can operate using patterns rather than pieces, relationships rather than components. It demonstrates that complexity can emerge from rules applied to fields without requiring complex building blocks. As experiments push further into extreme regimes and observations reach deeper into the cosmos, the photon continues to behave in the same way. It neither surprises nor deviates. Its simplicity holds. This consistency gives confidence that the field-based description is not provisional, but fundamental. With this understanding, the original question can finally be answered in precise terms. A photon is not made of matter. It is not made of smaller particles. It is not made of energy in the way objects store energy. A photon is a quantum of the electromagnetic field. It is a single, indivisible expression of how that field carries energy through space and time. This answer does not reduce the photon to nothing. It elevates it to something more basic. The photon is not a thing inside the universe. It is one of the ways the universe behaves. Although the photon is defined most cleanly through theory, its nature has been shaped and confirmed by measurement. Nearly everything known about photons comes from how they interact with instruments, matter, and spacetime. These interactions do not reveal an interior. They reveal consistency. Over time, this consistency has become one of the strongest arguments for the field-based description. Every detector that measures light operates on the same principle. It responds not to an incoming object, but to an energy transfer. Whether the detector is a silicon sensor, a superconducting bolometer, a photographic plate, or a biological molecule in the eye, the event is always discrete. The detector absorbs a specific amount of energy and responds accordingly. Nothing in the response suggests that the energy arrived gradually or that it was released from internal components. This discreteness was one of the earliest clues that light could not be described solely as a classical wave, but it also provided insight into the absence of structure. If a photon contained internal elements, detectors might show partial responses or variable energy deposits. Instead, the response is always complete. The entire quantum arrives at once. Advances in detector technology have sharpened this conclusion. Modern instruments can detect single photons with extraordinary precision. They can measure arrival time, energy, and polarization. Across countless experiments, no additional features have appeared. There is no signature of an internal clock, no evidence of internal vibration, no trace of delayed release. The photon arrives, interacts, and is gone. Time-resolved measurements reinforce this picture. When photons interact with matter, the interaction occurs within the limits allowed by quantum uncertainty. There is no measurable duration during which a photon slowly unloads its energy. The transfer is abrupt. This behavior matches the idea that the photon is not a container, but an indivisible event. Spatial measurements tell the same story. While detectors record a localized interaction, experiments show that the probability distribution associated with a photon can extend over large regions before detection. Interferometers reveal correlations that span meters, kilometers, or more. Yet the final interaction always occurs at one location. This combination cannot be explained by an object with a fixed size. It follows naturally from a field excitation whose interaction is quantized. The precision of spectral measurements offers another window. Atomic emission lines are among the most accurately measured quantities in physics. The frequencies of photons emitted during atomic transitions match theoretical predictions to extraordinary accuracy. If photons possessed internal degrees of freedom, those degrees would introduce tiny variations. None are observed. The sharpness of these lines speaks to the simplicity of the photon. The same is true for absorption. Atoms absorb photons only when the energy matches a specific transition. The photon does not adjust itself to fit the atom. Either the field excitation matches the allowed change, or no interaction occurs. This all-or-nothing behavior reflects a photon whose identity is fully specified by its energy and polarization, not by adjustable internal features. Quantum optics experiments deepen this understanding. In carefully controlled settings, researchers produce photons one at a time and guide them through complex optical systems. Beam splitters, mirrors, cavities, and nonlinear crystals alter how the field propagates. Yet at no point does a photon display behavior suggesting internal complexity. The results are always consistent with transformations applied to the field itself. Entanglement experiments provide another perspective. When pairs of photons are created together, their properties can become correlated. Measurements performed on one photon influence the statistical outcomes of measurements on the other. These correlations do not require communication or shared internal parts. They arise from the joint state of the electromagnetic field at the moment of creation. The photons themselves remain simple excitations. Importantly, entanglement does not introduce structure into the photon. It links outcomes without adding components. Each photon remains defined by the same minimal set of properties. The correlations exist in the field description, not inside the particles. Precision tests of relativity also rely on photon behavior. Experiments measuring time dilation, length contraction, and the invariance of the speed of light depend on photons behaving identically, regardless of energy. Any internal structure would introduce deviations. The continued success of these tests reinforces the view that photons are governed by field symmetries rather than by composition. In gravitational experiments, photons serve as probes of space-time curvature. Light traveling near massive objects bends and redshifts in ways predicted by general relativity. These effects do not distort the photon. They alter how the field is measured by observers in different frames. Once again, the photon behaves as a consistent excitation responding to external geometry. The convergence of evidence from detectors, spectroscopy, quantum optics, relativity, and astrophysics leaves little room for alternative interpretations. The photon behaves as a unitary, structureless excitation whose properties are fixed by the electromagnetic field. No experiment has required a more complicated description. This does not mean the photon is trivial. On the contrary, its simplicity enables complexity elsewhere. Because photons interact cleanly and predictably, they can mediate forces, encode information, and connect distant systems. The absence of internal structure makes them ideal carriers. The reliability of light underpins much of modern science. Telescopes rely on photons to bring information from the edge of the observable universe. Communication systems rely on photons to transmit data across vast distances. Quantum technologies rely on photons to preserve coherence and entanglement. None of this would be possible if photons contained hidden mechanisms prone to disturbance. As the experimental record continues to grow, the description of the photon becomes increasingly constrained. There is no room left for layers, shells, or subcomponents. Every measurable property is accounted for by field behavior. Every test reinforces the same conclusion. The photon, therefore, stands as a reference point. It shows how far physics can go by describing nature in terms of fields and their excitations. It demonstrates that not everything must be built from smaller pieces. Some things exist only as patterns of change. This understanding prepares the ground for a final reflection. If the photon is not made of anything, and if its existence depends entirely on field behavior, then the deeper structure of the universe may also be better described in terms of relationships and patterns rather than objects and substances. The photon offers a glimpse of this deeper layer. One of the most revealing roles the photon plays in modern physics is as a carrier of information. Nearly everything known about the universe beyond immediate reach arrives encoded in light. Distances, motions, temperatures, chemical compositions, and magnetic structures are inferred from photons that have traveled immense spans of space. The reliability of this information rests on the photon's lack of internal structure. There is nothing inside it that can selectively distort or rearrange the message it carries. Information carried by photons is not stored in material form. It is encoded in measurable properties such as frequency, phase, polarization, and timing. These properties arise directly from the electromagnetic field. When a photon is emitted, the field configuration reflects the conditions of its origin. As the photon propagates, those features remain intact unless altered by interaction with another system. This persistence allows information to survive journeys that last billions of years. Spectroscopy illustrates this with exceptional clarity. Light emitted by atoms carries signatures of specific energy transitions. These signatures appear as sharp spectral lines that can be identified across cosmic distances. The same atomic fingerprints observed in laboratories on Earth are detected in the light from distant stars and galaxies. This consistency would be impossible if photons possessed internal degrees of freedom capable of changing independently during flight. Timing measurements provide another example. Pulsars emit light in highly regular intervals. Photons from these sources arrive with extraordinary precision, allowing astronomers to track changes in rotation, motion, and gravitational influence. Any internal mechanism within the photon would introduce noise or drift. Instead, the timing remains stable, reinforcing the idea that the photon carries information without internal interference. Quantum information experiments push this reliability to its limits. Single photons are used to transmit quantum states between distant locations. The success of these experiments depends on the photon maintaining coherence. The absence of internal structure allows coherence to persist longer than it would in more complex particles. Decoherence arises from interaction with the environment, not from internal dynamics. This role as an information carrier reveals something deeper about measurement itself. In physics, measurement is not a passive act. It involves interaction. When a photon is measured, the electromagnetic field exchanges energy with matter. The outcome reflects both the state of the field and the properties of the measuring device. The photon does not reveal a hidden interior. It participates in an interaction governed by field rules. This perspective dissolves the idea that measurement uncovers pre-existing attributes inside the photon. Properties such as position are not stored internally waiting to be revealed. They are defined through interaction. The field configuration determines probabilities. The act of measurement selects an outcome. The photon's simplicity makes this process transparent rather than mysterious. Attempts to assign classical attributes to photons often run into difficulty because classical objects carry properties independently of observation. Photons do not. Their properties emerge through interaction with the field and with measuring systems. This does not imply incompleteness. It reflects the fact that photons are not objects in the classical sense. The same reasoning applies to localization. Before detection, a photon cannot be said to occupy a precise point. It exists as a field excitation spread according to the rules of propagation. Detection localizes the energy transfer, not the photon as an object. The distinction matters because it removes the need to imagine a particle traveling along a hidden trajectory. This field-centered view also clarifies why certain questions remain ill-defined. Asking where a photon is between emission and detection assumes it must occupy a specific place. Quantum field theory does not support this assumption. The photon exists as a possibility encoded in the field until interaction occurs. The field itself is what persists. In this sense, the photon serves as a boundary case for understanding reality. It forces a separation between description and intuition. Intuition evolved to deal with objects that persist, collide, and occupy space. The photon does none of these things in a classical way. Yet it is real, measurable, and indispensable. The absence of internal structure is what allows the photon to occupy this role. Without parts, there is nothing to rearrange. Without mass, there is nothing to resist motion. Without size, there is nothing to collide. The photon is defined entirely by relationships, how the field changes, how energy moves, how interactions occur. This relational character aligns with a broader trend in physics. Modern theories increasingly describe reality in terms of interactions and symmetries rather than substances. Conservation laws arise from symmetries. Forces arise from fields. Particles arise as excitations. The photon exemplifies this framework in its simplest form. The history of physics reflects a gradual shift toward this view. Early models treated light as a wave in a medium. Later, models treated it as a stream of particles. Quantum field theory unified these views by placing the field at the center. The photon emerged not as a compromise, but as a consequence. Even today, the photon continues to shape new developments. Advances in quantum communication, precision measurement, and astrophysical observation all rely on its properties. As technology improves, experiments probe ever smaller effects. Yet the photon continues to behave exactly as predicted by the simplest description available. This persistence suggests that the photon is not hiding additional layers waiting to be discovered. Instead, it represents a case where nature has already revealed the most economical description possible. Additional complexity would not improve explanatory power. It would conflict with observation. From this vantage point, the photon becomes a guide. It shows how much can be understood by focusing on how fields behave rather than on what objects are made of. It demonstrates that energy, information, and interaction can exist without material carriers. As the script approaches its conclusion, the question that opened this exploration can be reconsidered with clarity. What is a photon made of? The evidence gathered across experiments, observations, and theory points consistently to the same answer. A photon is not made of matter. It is not made of smaller parts. It is made of change. Change in the electromagnetic field constrained by quantization and symmetry is sufficient to produce everything the photon does. Nothing more is required. This answer does not diminish the photon. It reveals why it is so effective. The final step is to place this understanding back into the broader context of the universe. Light connects distant events, shapes cosmic history, and enables observation itself. All of this rests on the existence of a simple excitation that carries energy without structure. The photon stands as a reminder that the universe often operates not through elaborate machinery, but through minimal rules applied consistently. When viewed across the full span of modern physics, the photon occupies a role that is both ordinary and exceptional. Ordinary because it appears everywhere. Exceptional because nothing else behaves in quite the same way. It is present in nearly every physical process, yet it leaves almost no trace of its own identity beyond the effects it produces. Stars shine by emitting photons. Atoms exchange energy through photons. Chemical reactions depend on photons. Even the structure of matter is influenced by electromagnetic interactions mediated by photons. Despite this ubiquity, the photon itself resists every attempt to be treated as a conventional object. It does not persist as matter does. It does not accumulate. It does not carry a history within itself. This absence of history is important. A photon emitted in one environment is indistinguishable from a photon emitted in another, provided their measurable properties match. There is no internal record of where the photon has been. Its past does not imprint itself on its future behavior. This is another consequence of having no internal structure. There is nothing inside the photon that can store memory. Contrast this with matter. A piece of matter carries the imprint of its formation. Defects, excitations, and internal states influence how it behaves later. Photons carry no such imprint. Their behavior is determined entirely by the field configuration at the moment of interaction. This makes them uniquely reliable messengers. The concept of reliability becomes especially important when considering cosmology. Much of what is known about the early universe comes from photons that have traveled for nearly the entire age of the cosmos. These photons preserve information about conditions that no longer exist. Their frequencies, directions, and polarization patterns encode data about density fluctuations, temperatures, and motions from the universe's earliest eras. If photons contained internal complexity, this information would be degraded beyond recognition. The fact that it remains accessible is strong evidence that the photon is structurally minimal. The electromagnetic field does not accumulate internal noise as it propagates its excitations. The signal remains readable. This clarity has allowed physicists to test theories that operate at the largest scales. General relativity predicts how light should move through curved spacetime. Observations of gravitational lensing, redshift, and time delay confirm these predictions with high accuracy. The photon acts as a tracer of space-time geometry, not as a participant with its own internal response. At the smallest scales, the photon plays an equally important role. In quantum electrodynamics, interactions between charged particles are described in terms of photon exchange. These descriptions produce predictions that match experiments to astonishing precision. The agreement is so close that any deviation would be immediately apparent. No deviation has been found. This success is not accidental. It depends on the photon being exactly what the theory describes: a massless, structureless excitation of a field with well-defined symmetry properties. Any additional structure would introduce corrections that experiments would detect. The absence of such corrections reinforces the simplicity of the photon. The photon's lack of rest mass also shapes the structure of physical law. Because photons always move at the same speed, they provide a universal reference. This property underlies the structure of relativity. The speed of light is not merely a property of photons. It is a property of space-time itself, revealed through the behavior of electromagnetic field excitations. In this sense, the photon acts as a bridge between quantum theory and relativity. It embodies principles from both domains. Its quantization reflects quantum structure. Its constant speed reflects space-time geometry. Its behavior connects the two frameworks in a way few other entities do. This bridging role has guided theoretical development. Many attempts to unify physics rely on extending the field-based description to other interactions. While these efforts remain incomplete, the photon provides a model of how such a unification might look. Simple excitations governed by symmetry and quantization can give rise to rich phenomena without requiring complex internal composition. The idea that simplicity underlies complexity runs counter to common intuition. It is natural to imagine that complex behavior must arise from complex components. The photon suggests otherwise. Complex patterns can emerge from simple rules applied to fields that extend everywhere. This lesson extends beyond physics. It influences how models are constructed, how explanations are evaluated, and how assumptions are tested. The photon demonstrates that adding structure is not always the path to understanding. Sometimes removing assumptions reveals a clearer picture. As experimental techniques continue to advance, physicists probe regimes where new behavior might emerge. Yet the photon continues to behave exactly as expected. It does not surprise. It does not reveal hidden layers. It remains consistent across energies, distances, and environments. This consistency has philosophical implications, though it arises from empirical facts rather than speculation. It suggests that the universe may not be built from discrete objects in the way everyday experience implies. Instead, it may be built from continuous fields whose excitations manifest as particles when energy moves. In this view, matter itself becomes a special case. Matter corresponds to field configurations that are stable and localized. Light corresponds to configurations that are transient and propagating. Both arise from the same underlying framework. The difference lies not in substance, but in pattern. The photon therefore challenges the language used to describe reality. Words like object, particle, and thing carry assumptions that do not apply cleanly. The photon forces a more careful vocabulary, one that emphasizes process, interaction, and relation over composition. As this exploration draws toward its final stages, the central insight remains steady. The photon does not need to be dismantled to be understood. It does not conceal smaller elements. Its behavior is fully accounted for by the structure of the electromagnetic field and the rules that govern it. The question of what a photon is made of thus resolves into a question of how the field behaves. And the answer, supported by a century of experiment and theory, is remarkably simple. The photon is a quantum of change. Change in the electromagnetic field, constrained by symmetry, quantization, and space-time geometry, is sufficient to produce light in all its forms. From the faint glow of distant galaxies to the focused beam of a laser, the same principle applies. With this understanding, the photon becomes not an exception to physical intuition, but a guide toward a deeper one. It shows that the universe does not require hidden machinery to function. It requires only consistent rules applied to fundamental fields. When the question of composition is asked in physics, it usually leads to deeper layers. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. At each stage, structure gives way to finer structure. The photon breaks this pattern. Every attempt to probe it more deeply has returned the same result. There is no smaller layer waiting beneath. This does not mean that the photon is primitive in the sense of being crude or incomplete. It means that it is fundamental in a different way. It is not assembled from constituents. It is defined by the rules that govern the electromagnetic field. Its properties arise from symmetry, quantization, and geometry, rather than from internal arrangement. The persistence of this result across decades of investigation is significant. Particle accelerators have pushed interactions to energies far beyond those found in ordinary matter. Astronomical observations have tracked photons across most of the observable universe. Precision experiments have measured electromagnetic processes to extraordinary accuracy. None have uncovered evidence of substructure within the photon. In science, absence of evidence is not always evidence of absence. But when absence persists across independent methods, scales, and environments, it becomes meaningful. In the case of the photon, the absence of internal structure is not a gap in knowledge. It is a conclusion supported by converging lines of evidence. The photon, therefore, occupies a position unlike that of most particles. It is not characterized by a list of internal features. It is characterized by constraints. It must travel at a fixed speed. It must carry energy proportional to frequency. It must exhibit only two helicity states. It must interact in discrete events. These constraints define it completely. This constraint-based identity reflects the nature of fields. Fields are not objects that can be opened or dismantled. They are systems defined by how they respond to change. The electromagnetic field supports certain patterns and forbids others. The photon is one of the allowed patterns. Its simplicity reflects the simplicity of the underlying field. The lack of decay channels further illustrates this point. Many particles can transform into lighter ones because their internal configurations allow energy to rearrange. The photon has no internal configuration to rearrange. It can disappear only by transferring its energy to another system. As long as no interaction occurs, the photon persists indefinitely. This persistence does not imply durability in a material sense. It implies stability of pattern. The electromagnetic field maintains the excitation unchanged as it propagates. There is nothing inside the photon that can erode. There is no mechanism for gradual loss. The field either carries the excitation or it does not. The same reasoning applies to the question of boundaries. Objects have edges because they occupy space. The photon does not occupy space in that way. It exists as a pattern distributed across the field. Its extent is defined by propagation, not by containment. Asking where the photon ends is like asking where a wave ends. The answer depends on context, not on structure. As physics has matured, this way of thinking has become increasingly common. Concepts once associated exclusively with objects are now understood as emergent features of fields. Mass, charge, and spin arise from interactions and symmetries. The photon exemplifies this shift more clearly than any other particle. It also highlights the limits of metaphor. Language developed to describe solid objects struggles to capture entities that are neither solid nor persistent. Terms like particle and wave are approximations. They describe aspects of behavior, not composition. The photon resists being placed fully into either category because it does not belong to the conceptual framework from which those categories arose. This resistance is not a failure of understanding. It is a sign that the framework has changed. Quantum field theory replaces the idea of particles as basic building blocks with a picture in which fields are fundamental and particles are secondary. The photon is one of the simplest expressions of this idea. Within this framework, the photon has no need for an inside. Its identity is complete without it. Everything observable about the photon follows from how the electromagnetic field behaves when energy is present in a quantized form. There are no missing pieces to fill in. This understanding also clarifies why attempts to visualize photons often lead to confusion. Diagrams that depict photons as tiny dots or arrows can be useful, but they are representations, not literal pictures. The photon does not resemble these images any more than a magnetic field resembles lines drawn on paper. The images capture relationships, not structure. The practical success of physics does not depend on visualizing photons correctly. It depends on predicting their behavior. In this regard, the field-based description has been extraordinarily successful. It allows engineers to design lasers, physicists to build detectors, and astronomers to interpret signals from distant galaxies. None of these applications require a picture of internal composition. As the exploration of nature continues, new particles may be discovered and new fields proposed. Some may possess internal structure. Some may reveal unexpected complexity. The photon has already been tested across a wider range of conditions than almost any other entity. Its behavior remains unchanged. This stability gives the photon a special status. It serves as a reference against which other phenomena are measured. It anchors theories and constrains speculation. Any new model of physics must reproduce the photon exactly as observed. There is no flexibility here. The question of what a photon is made of therefore resolves into a statement about how physics describes reality. Some things are made of parts, others are not. Some exist as objects, others exist as processes. The photon belongs firmly in the second category. It is not an object moving through space. It is not a container of energy. It is an event, a transfer, a quantized change in a field that fills all of space. Its properties arise from rules, not from ingredients. In this light, the photon becomes less mysterious and more instructive. It shows that the deepest layers of reality may not resemble the objects encountered in everyday life. They may instead resemble relationships and patterns that only become tangible through interaction. With this perspective, the original question no longer demands a list of components. It invites a shift in thinking. The photon is not made of something. It is what happens when the electromagnetic field changes in the smallest possible way. Seen in the full context of modern physics, the photon serves as a boundary marker between classical intuition and field-based reality. It occupies the point where everyday concepts begin to fail, and more abstract principles take over. This is not because the photon is obscure or exotic, but because it is too simple to fit comfortably into object-centered thinking. Classical physics describes the world in terms of entities that persist through time. They have positions, trajectories, and internal states. Even waves, though spread out, are usually tied to a medium that carries them. The photon does not fit either picture. It persists only as long as energy is being transported. It has no independent existence beyond that process. This has consequences for how causality is understood. When light is emitted, it does not carry a miniature copy of its source. It carries information encoded in field relationships. When it is absorbed, that information is transferred without residue. The photon does not mediate causation through impact, but through correlation between field states. This distinction becomes important in quantum experiments where cause and effect appear counterintuitive. Delayed choice experiments, interference with single photons, and entanglement tests often provoke confusion because they are interpreted using object-based assumptions. When the photon is understood as a field excitation, these results appear less paradoxical. The field evolves according to rules. Interactions select outcomes. No hidden trajectory is required. The photon also clarifies the role of symmetry in physics. Many of its properties follow directly from symmetry principles rather than from dynamics. The fact that it has two helicity states follows from rotational symmetry combined with masslessness. The fact that its energy is proportional to frequency follows from time translation symmetry. These are not accidental features. They are consequences of how the electromagnetic field is structured. Because symmetry plays such a central role, the photon acts as a test of fundamental principles. Any proposed change to physical law must preserve these symmetries or explain why they break. The absence of observed deviations places strong constraints on new theories. The photon's simplicity limits how much physics can change without contradiction. In this way, the photon becomes a stabilizing element in theoretical exploration. It does not merely participate in physical processes. It enforces consistency. It demands that explanations align with observed invariances. This makes it both a tool and a constraint. The connection between photons and space-time further deepens this role. The speed at which photons propagate is not just a feature of electromagnetism. It defines the causal structure of space-time itself. Events that can influence one another are connected by paths that photons could follow. This places the photon at the foundation of how time and space are organized. Yet, despite this foundational role, the photon itself remains free of internal structure. It shapes the framework without being shaped by it. It reveals geometry without carrying geometry inside itself. Once again, this reinforces the idea that its properties arise from rules rather than from composition. The development of physics has often involved moving away from mechanical pictures toward abstract ones. Planets were once imagined as carried by spheres. Fields replaced forces acting at a distance. Quantum theory replaced trajectories with probabilities. The photon fits naturally into this progression. It is not the failure of imagination, but the success of abstraction. Importantly, abstraction does not imply detachment from reality. The field description of the photon produces concrete predictions that can be tested and used. Technologies built on this understanding operate reliably because the underlying description is accurate. The lack of internal structure is not an omission. It is a feature that enables precision. As research continues, photons are being used in increasingly refined ways. Single photon sources, quantum networks, and precision clocks all rely on the same basic properties discussed throughout this exploration. None of these applications suggest hidden complexity. Instead, they exploit simplicity. The photon's behavior also influences how limits are understood. There is a smallest unit of electromagnetic energy transfer. There is a fastest possible propagation speed. There is no smaller subdivision of light. These limits are not arbitrary. They arise naturally from the structure of the field. By encountering these limits, physics gains clarity about what questions are meaningful. Asking how to split a photon further is like asking how to split a unit of change. the question does not apply. The photon marks the point at which division ends. This realization has educational value as well. It shifts focus from searching for ever smaller pieces to understanding deeper principles. The photon teaches that not all fundamental entities are composed. Some are defined by constraints and relationships alone. As this understanding settles, the original question transforms completely. What is a photon made of becomes less a query about substance and more a prompt to examine assumptions. It reveals the limits of object-based thinking and the reach of field-based explanation. The photon does not hide its nature behind inaccessible scales. It reveals it openly through behavior. The absence of internal structure is not inferred from ignorance, but from consistency. Every test that could reveal complexity has instead confirmed simplicity. In this sense, the photon stands as one of the clearest lessons modern physics offers. Nature does not always build from pieces. Sometimes it builds from rules. Sometimes what exists is not an object, but an action permitted by a field. This lesson does not end with light. It extends to how matter, forces, and space-time itself may ultimately be understood. The photon provides a glimpse of that deeper structure, where patterns replace parts and relationships replace components. With this perspective, the story of the photon becomes complete. It begins with an everyday phenomenon, light, and ends with a fundamental insight about reality. The photon is not made of anything in the conventional sense. It is the smallest possible expression of how the electromagnetic field changes. By this stage, the photon no longer appears as a strange exception within physics, but as a reference point that clarifies how the universe organizes itself. Many of the most puzzling questions in modern science become easier to approach once the photon is understood correctly. Its behavior strips away assumptions that arise from everyday experience and replaces them with principles grounded in fields, symmetry, and interaction. One of the most important lessons comes from how the photon relates to energy itself. In classical thinking, energy is something objects possess. In field-based physics, energy is something fields do. The photon demonstrates this distinction cleanly. Its energy does not reside inside it as a stored quantity. It exists in the ongoing configuration of the electromagnetic field as it propagates. This explains why a photon cannot be partially absorbed. Either the field transfers the full quantum of energy or it does not. There is no mechanism for dividing the excitation because there is no container to open. The energy transfer is a single event governed by the rules of the field. This behavior is observed universally, from atomic transitions to high-energy particle collisions. The same reasoning applies to momentum. A photon delivers momentum despite having no mass, because momentum, like energy, is a property of fields as well as matter. When the electromagnetic field changes in a directed way, momentum is present. The photon carries that momentum as part of its propagation. Nothing inside it pushes. The field itself enforces conservation. This field-centered view also clarifies why photons interact the way they do. When light scatters, reflects, refracts, or is absorbed, these processes are not collisions between objects. They are adjustments in field configurations. The photon participates by allowing energy and momentum to move between systems. Once that transfer occurs, the excitation ends. Importantly, this means that photons are not persistent entities traveling from source to destination unchanged in a material sense. They persist only as long as the field maintains that excitation. When absorption occurs, the photon does not transform or decay. It ceases to exist as a photon because the field no longer supports that particular pattern. This idea removes a common misconception. Photons are not tiny bullets fired from atoms. They are not parcels thrown through space. They are changes in the field that propagate according to precise rules. The bullet analogy persists because it helps describe detection, but it obscures propagation. Understanding the difference is essential. The electromagnetic field itself deserves attention here. It is not an abstract mathematical convenience. It is a physical entity with measurable effects. It carries energy, responds to charges, and influences space-time through gravity. The photon is one way this field manifests when energy is exchanged. Without the field, the photon has no meaning. This dependence on the field explains why photons cannot exist in isolation from the rest of physics. Their properties arise from the structure of space-time, the symmetries of the field, and the conservation laws that govern interaction. Remove any of these elements, and the concept of a photon collapses. The clarity provided by the photon also helps distinguish between meaningful and meaningless questions. Asking what a photon is made of assumes composition. Asking how a photon behaves asks about rules. Physics answers the second question completely and finds no need for the first. This distinction matters because it highlights a broader shift in scientific explanation. Early science focused on substances and mechanisms. Modern physics focuses on relationships and constraints. The photon exemplifies this shift more cleanly than any other entity studied so far. It also reveals why attempts to imagine deeper layers beneath the photon have repeatedly failed. There is no room for smaller pieces because the description already operates at the level of allowed change. Any proposed substructure would have to introduce new degrees of freedom. Those degrees of freedom would alter behavior. No such alterations are observed. The photon therefore marks a natural stopping point in the search for components. This does not mean physics ends here. It means that explanation changes form. Instead of asking what things are made of, physics asks what patterns are allowed and why. This way of thinking aligns with how modern theories are constructed. Gauge symmetries define interactions. Conservation laws define possible processes. Fields define what can exist. Particles appear as consequences, not causes. The photon sits comfortably within this framework. Even speculative theories that extend beyond established physics must respect the photon's behavior. Proposals involving extra dimensions, quantum spacetime, or modified symmetries are tightly constrained by the observed properties of light. The photon's simplicity limits how far speculation can go without contradiction. This role as a constraint is as important as the photon's role as a messenger. It keeps theory grounded. It prevents unfounded complexity. It ensures that new ideas remain connected to observation. As this exploration approaches its conclusion, one theme remains constant. The photon does not become clearer by adding layers. It becomes clearer by removing assumptions. Once those assumptions fall away, the photon emerges not as a puzzle, but as a demonstration of how deeply fields shape reality. What remains is to bring this understanding to a final resolution, not by summarizing facts already established, but by answering the original question in its most precise and complete form, using the language that modern physics actually supports. The question that guided this entire exploration was simple in form, but deep in implication. What is a photon made of? At the beginning, that question seemed to demand a list of components, some internal substance, or a hidden structure waiting to be revealed. By following the evidence step by step, the question itself has changed. Every attempt to treat the photon as a constructed object fails. It has no rest mass to anchor it, no size to bound it, no internal states to rearrange, no decay channels to exhaust, and no measurable substructure. It cannot be opened because there is nothing inside it. It cannot be divided because it is already the smallest possible unit of its kind. What remains after all assumptions are removed is not emptiness, but clarity. The photon is not made of matter. It is not made of energy as a stored substance. It is not assembled from smaller pieces. A photon is a quantum of the electromagnetic field. It is a single, indivisible expression of how that field carries energy, momentum, and angular momentum through space and time. This answer does not rely on interpretation or philosophy. It follows directly from observation. Photons behave identically across laboratories, stars, galaxies, and the early universe. They obey the same relationships, respond to the same symmetries, and exhibit no variation that would suggest hidden complexity. The simplest description is not an approximation. It is the correct one. Modern physics therefore treats the photon not as an object moving through space, but as a process unfolding within a field. When energy is transferred electromagnetically, the field changes in a quantized way. That change propagates. While it propagates, it is called a photon. When the energy is absorbed, the excitation ends. Nothing is left behind because nothing was contained. In this sense, the photon does not exist in the way matter exists. It exists only as motion, only as change, only as a permitted pattern within a field that fills the universe. It is defined entirely by rules rather than by ingredients. This understanding resolves every major feature discussed along the way. Wave behavior arises because fields propagate continuously. Particle behavior arises because energy exchange is quantized. Spin arises from symmetry, not rotation. Energy arises from frequency, not mass. Size dissolves into probability and propagation. Stability arises from the absence of internal parts. The photon is therefore not mysterious because it hides complexity. It is striking because it does not require any. It demonstrates that the universe does not always build from smaller and smaller pieces. Sometimes it builds from constraints, symmetries, and allowed changes. Light becomes understandable not as a stream of objects, but as the visible expression of one of the universe's most fundamental fields in motion. The photon is the smallest step that motion can take. When asked what a photon is made of, modern physics gives a precise answer. A photon is not made of anything else. It is what happens when the electromagnetic field changes in the smallest possible way allowed by nature. And with that, the question reaches its end.